Major Richard Kuhn banks the B-52G into its third refueling track, 30,000 feet above Baffin Bay. 22 hours into a sortie that began before dawn yesterday. 4 live hydrogen bombs clamped in the weapons bay 6 feet below his seat. Fuel gauges showing 3 hours to bingo if the tanker misses the rendezvous window. The boom operator's voice crackles over HF radio, calling distances in hundreds of feet. Kuhn hand-flies the aircraft because the autopilot cannot track the tanker's refueling probe, and his co-pilot's reaction time is already slipping after 22 consecutive hours at altitude. The mission calls for 24 hours aloft, 6 refuelings, and continuous orbit near Soviet airspace. No inspection of the weapons bay, no rest, no margin for error. Earlier that day, Kuhn and his 6-man crew rolled down the Loring Air Force Base runway at 0400 hours, with 4 Mark 28 hydrogen bombs and enough fuel for 4 hours. The mission plan called for 6 more refuelings and 24 continuous hours aloft before they could land. Each weapon weighed 1,600 pounds and carried a plutonium core wrapped in high-explosive lenses. The bombs hung on quick-release shackles designed to drop them on target in seconds. But for the next 24 hours, those shackles had to hold through turbulence, thermal cycles, and vibration that no ground test could replicate. The flight plan traced a racetrack orbit from Baffin Bay to the Greenland coast. Always within 2 hours of Soviet airspace. Always close enough to receive fail-safe authentication codes over high-frequency radio. The route kept the bomber in international airspace, but close enough to strike targets deep inside the USSR if the order came. Kuhn's navigator, Lieutenant Pell, updated wind drift and calculated fuel margins every 30 minutes because a 20-knot headwind error could leave them short of the next tanker rendezvous. Missing a tanker meant ditching in the Arctic Ocean with 4 live nuclear weapons aboard. Kuhn's co-pilot, Captain Diaz, monitored 8 Pratt & Whitney J-57 turbojets, each burning 700 gallons per hour. That meant 5,600 gallons every 60 minutes, or 93 gallons per minute, pouring through combustion chambers that ran hot enough to melt steel if the fuel flow stuttered. The engines had no backup igniters in flight. If one flamed out during refueling, the aircraft would lose thrust asymmetrically and yaw into the tanker's boom. Diaz scanned exhaust gas temperatures and fuel pressure gauges every 2 minutes, watching for the early signature of a compressor stall or turbine crack that could cascade into total failure before the next refueling cycle. Below the crew compartment, the 4 weapons hung on quick-release shackles. Thermal batteries and explosive lenses sat inches beneath the flight deck, with no way to inspect or disarm them until landing. The bombs were designed to be stable, but stability assumed ground storage or a short flight to target, not 24 hours of vibration and thermal cycling between minus 40 degrees Fahrenheit at altitude and cabin heat radiating through thin aluminum floors. A hydraulic leak or fuel drip onto a bomb casing could ignite the explosive lens without triggering any cockpit warning. The crew would know only when the blast tore through the pressure hull. Strategic Air Command had kept at least 1 Chrome Dome sortie airborne every hour of every day since 1960. Kuhn's crew was one of 12 rotating through Loring on 4-hour alert cycles, living in a cinder block ready room between missions. The ready room held cots, a coffee urn, and a wall-mounted status board showing which crews were airborne, which were on deck, and which were in mandatory crew rest. 4 hours on alert, 24 hours flying, 4 hours post-flight debrief and maintenance inspection, then back to the ready room. The cycle repeated for months until rotation back to stateside duty or a different alert base. By hour 12, both pilots had hand-flown the aircraft through 4 refueling contacts. The B-52's autopilot could hold altitude and heading, but could not track the tanker's boom, so every refueling demanded full manual control at 30,000 feet. The process took 20 minutes per contact, close to within 50 feet of the tanker's tail. Match speed within 2 knots. Hold position while the boom operator guided the probe into the receptacle, then maintain formation for 10 minutes while fuel transferred. A gust or a moment of inattention would slam the boom into the fuselage or shear the receptacle fitting, ending the sortie and possibly igniting the fuel vapor. The navigator had no way to verify that the bomb bay thermal batteries remained stable or that the weapon shackles had not vibrated loose. A fuel leak or hydraulic drip onto a bomb casing could ignite the explosive lens without triggering any cockpit warning. The weapons were designed with thermal buffers and protective coatings, but those were tested in controlled ground environments, not in a vibrating bay that cycled between Arctic cold and engine exhaust heat every few hours. If a battery overheated or a shackle pin backed out, the first indication would be a catastrophic explosion or a bomb tumbling free during the next banking turn. At hour 16, Kuhn took his second dextroamphetamine tablet from the flight surgeon's kit. The co-pilot's reaction time was already degraded, and they still faced 2 more refuelings and the fail-safe decision point over the Norwegian Sea. The tablets were 5 milligrams each, enough to suppress sleep pressure, but not enough to eliminate the microsleeps that crept in during instrument scans. Kuhn had seen pilots miss altitude deviations or fuel imbalances after 20 hours aloft, despite the amphetamines. The drug kept you awake, but it could not restore decision-making speed or fine motor control. Those required sleep, and sleep was not part of the mission plan. The fail-safe point was a set of coordinates where the crew must receive an authenticated go code within 4 minutes or turn back. A garbled transmission, a misheard letter, or a stuck microphone button could send them into Soviet airspace without valid orders, or abort a real attack. The navigator held a code card printed on red paper that would dissolve if exposed to water or excessive heat. The pilot listened for a specific phonetic sequence over HF radio. Both had to agree the code matched before crossing the line. 4 minutes to decide whether to start World War III or commit treason. The aircraft had no redundant communication system. 1 HF radio, 1 code card, and 4 minutes to decide whether to start World War III or commit treason. If the radio failed, the crew was supposed to turn back. But turning back during a real Soviet first strike would leave American command vulnerable and possibly invite a second wave. If the code card was damaged or lost, there was no backup. The entire fail-safe procedure rested on a single fragile link between a fatigued crew and a command center thousands of miles away, with atmospheric interference, sunspot activity, and radio frequency noise between them. January 17, 1966. A B-52G out of Seymour Johnson Air Force Base completed its 6th refueling over the Mediterranean and began descent toward the Spanish coast. The boom receptacle failed to seal, streaming fuel vapor into the cabin heater intake. The seals were designed for 600 refuelings, but this aircraft had logged over 1,000 sorties, and the rubber gaskets had hardened in the cold. Fuel vapor is heavier than air, so it pooled in the heater ducts and flowed forward into the cockpit and navigator compartment, invisible but highly flammable. The pilots smelled fuel at 28,000 feet. The navigator saw vapor clouding the astrodome, but the fuel gauges still read normal, and the mission profile required them to stay airborne for 2 more hours. The aircraft commander, Major Larry Messenger, considered declaring an emergency and diverting to Morón Air Base in Spain, but the gauges showed no leak and the engines ran smoothly. Vapor without a measurable fuel loss suggested a minor seal issue that might clear on its own. Messenger decided to continue the descent and monitor the situation, because aborting a nuclear sortie over a suspected leak would trigger a full investigation and possible grounding of the entire Chrome Dome fleet. At 15,000 feet, the co-pilot reported smoke in the cockpit. The pilot called for an emergency descent into Morón Air Base, but the fire spread faster than the descent rate. The fire suppression system in the cockpit used halon gas that was effective on electrical fires, but not on fuel-fed flames. Smoke filled the forward compartment within 90 seconds, cutting visibility to less than 2 feet. The pilots donned oxygen masks and continued the descent, but the flight controls began to respond sluggishly as hydraulic lines running through the burning compartment lost pressure. The crew ejected at 4,000 feet. 6 men separated cleanly, but the bombardier's ejection seat failed, and he rode the aircraft into the ground near the village of Palomares. Ejection seats are designed to work between 200 and 35,000 feet, but the Bombardier's seat had a pyrotechnic initiator that had absorbed moisture during months of coastal operations and failed to ignite. The aircraft broke apart on impact, scattering debris and fuel across farmland. The Bombardier's body was found in the wreckage. The other 6 crew members landed by parachute in fields and coastal waters and were recovered by Spanish fishermen within an hour. 4 Mark 28 hydrogen bombs, each carrying a plutonium core and explosive triggers, fell from the disintegrating weapons bay across 2 square miles of Spanish farmland and coastal water. The weapons were not armed, none of the 6 interlocks had closed, but they fell from 15,000 feet without parachutes deploying on 3 of the 4. Impact velocity was roughly 200 miles per hour. The bombs hit soft soil, a riverbed, and shallow water. Local farmers heard the explosions and saw craters smoking in tomato fields. They had no idea they were standing next to hydrogen bombs. A Mark 28 thermonuclear bomb has 6 mechanical safing devices, a barometric sensor that arms below 18,000 feet, a timer that requires 90 seconds of freefall, an electrical interlock that needs cockpit release signal, a centrifugal switch that detects weapon spin, a thermal battery that powers the firing circuit, and a mechanical safe arm lever that must be rotated by the bombardier. Each interlock must close in the correct sequence or the weapon cannot detonate. The system was designed so that no single failure, no accidental drop, and no unauthorized release could produce a nuclear yield. But the design assumed the weapon would either fly safely to target or remain inert. It did not account for a crash that bypassed some interlocks while triggering others. The high explosive lens surrounding the plutonium pit is designed to compress the core into a supercritical mass only when all 6 interlocks close simultaneously. The lens is shaped to produce a converging shockwave that collapses the pit inward from all directions at exactly the same moment. If even one interlock fails open, the firing circuit cannot send the detonation signal to all lens segments at once, and the pit cannot achieve the symmetry required for a nuclear yield. Asymmetric compression scatters the plutonium instead of compressing it. The result is a high explosive detonation that blasts radioactive metal across the impact site, but no chain reaction and no mushroom cloud. On impact, 3 of the 4 Palomares weapons experienced 1-point safety failure. The explosive lens detonated from mechanical shock, blasting the plutonium pit into fragments without achieving criticality. The detonation scattered radioactive metal across the impact crater instead of producing a nuclear explosion. The high explosive produced craters 15 feet deep, throwing plutonium-contaminated soil hundreds of feet downwind. Local farmers and fishermen walked through the debris field within hours, unaware that the dust on their boots and clothing contained alpha-emitting isotopes. The 4th weapon landed intact in shallow water. Its parachute had deployed, slowing the descent enough that none of the interlocks closed and the explosive lens remained stable. The Air Force recovery team had no procedure for locating plutonium fragments in soil. The standard Geiger counters detected gamma radiation, but plutonium-239 emits alpha particles that travel only inches in air. Alpha particles cannot penetrate skin or even a sheet of paper, so contaminated dirt looked clean unless you dug it up and tested it in a lab. Survey crews drove over fields with vehicle-mounted detectors and found nothing. Meanwhile, farmers continued to work the land, plowing plutonium deeper into the soil with every pass. It took weeks to bring in sensitive alpha spectrometers and map the true contamination area, which turned out to be 6 times larger than the initial gamma survey suggested. Within 12 hours, EOD teams located 2 weapons intact in a riverbed and 1 crater with plutonium fragments embedded in tomato fields. The 4th weapon was missing, and the only witness was a fisherman who saw parachutes descending into the sea 5 miles offshore. The intact bombs in the riverbed were carefully lifted by crane and flown back to the United States for inspection. The crater weapon had disintegrated, leaving nothing but fragments and contaminated soil. The missing weapon became the focus of an international search that would eventually involve the U.S. Navy's deepest diving submersible, and 80 days of underwater search operations. The Air Force brought in oceanographer Dr. John Craven and the submersible Alvin to search a steep underwater slope in currents that shifted the weapon's position daily. The search took 80 days and nearly failed when Alvin's tether snagged the parachute shroud at 2,500 feet depth. The weapon had come to rest on a 45-degree slope covered in silt. Each dive took hours, and Alvin could stay down for only 9 hours before surfacing to recharge batteries. Craven used Bayesian search theory to narrow the probability zone, but the final location came from a fisherman's eyewitness account that placed the parachute descent 2 miles farther east than the initial search box. On land, cleanup crews scraped 1,600 tons of topsoil and shipped it to South Carolina in barrels. Alpha surveys later revealed plutonium hotspots the Geiger counters missed, leaving contamination that persists into the 21st century. The cleanup removed soil down to 2 feet depth across the highest contamination zones, but deeper plutonium had already leached into the groundwater table. Spanish authorities conducted follow-up surveys every decade. Traces of americium-241, a plutonium decay product, still appear in vegetation samples 50 years after the crash. The United States eventually paid millions of dollars in settlement to affected landowners, but the contamination itself could not be fully reversed. Strategic Air Command temporarily suspended Chrome Dome sorties over populated areas, but resumed full operations within 6 weeks, arguing that airborne alert remained essential to survivable deterrence. The calculus was strategic. Without airborne bombers, a Soviet first strike could destroy all ground-based alert aircraft before they launched. Keeping bombers aloft meant that even a surprise attack would leave the U.S. with enough airborne nuclear weapons to retaliate. The risk of another crash was acknowledged, but judged acceptable compared to the risk of losing the entire bomber force on the ground. For 2 more years, B-52s continued to fly 24-hour sorties with live nuclear weapons over the Arctic, the Atlantic, and the Mediterranean. 2 years later, on January 21, 1968, another B-52G on Chrome Dome suffered a cockpit fire over Greenland, crashed onto the ice 7 miles from Thule Air Base, and scattered 4 more hydrogen bombs across the frozen bay. The fire started in the co-pilot's crew rest compartment when a cushion ignited near a cabin heater outlet. The crew attempted to suppress the fire with portable extinguishers, but smoke filled the cockpit within minutes. The pilot ordered an emergency descent toward Thule, but the fire consumed the control cables before the aircraft could land. 6 crew members ejected successfully. The aircraft impacted sea ice at 300 miles per hour, breaking through into shallow water and igniting 20,000 gallons of jet fuel. 8 days after the Thule crash, Secretary of Defense Robert McNamara permanently ended Operation Chrome Dome. The Air Force transitioned nuclear alert to ground-based bombers and ballistic missile submarines, keeping weapons out of continuous flight. The decision was immediate and final. No gradual phase-out, no extended review. McNamara judged that 2 crashes in 2 years, both scattering plutonium across Allied or neutral territory, made the program politically and diplomatically unsustainable. Submarines offered continuous at-sea deterrence without the risk of crashing over populated areas. Ground alert meant bombers could still launch on warning, but they would not carry live weapons until after takeoff confirmation. Cleanup at Thule recovered plutonium debris from the ice, but an estimated 1 to 3 kilograms remains on the sea floor beneath the crash site, leaching into Arctic currents. Denmark demanded compensation and restricted U.S. nuclear overflights for the next 2 decades. The contamination was compounded by the fact that the crash occurred on winter sea ice that melted and refroze seasonally. Each melt cycle dispersed plutonium particles farther across the bay. Surveys in the 1990s detected elevated alpha activity in sediment cores up to 2 miles from the impact site. The plutonium will remain hazardous for thousands of years, outlasting any institutional memory of the accident. Spain conducted soil surveys at Palomares every decade. Traces of americium-241, a plutonium decay product, still appear in vegetation samples 50 years after the crash. And the United States paid millions of dollars in settlement to affected landowners. The contamination was not lethal in acute doses, but it represented a permanent increase in background radiation across roughly 2 square kilometers of farmland. Tomatoes, wheat, and barley grown in the area carried detectable alpha activity. Spanish authorities restricted some land from agriculture and continued to monitor groundwater wells. The cost of the settlements, the cleanup, and the decades of monitoring far exceeded the strategic value of any single Chrome Dome sortie.
Chrome Dome flew continuously for 8 years, logging tens of thousands of sorties without ever launching a nuclear attack. The program demonstrated that bombers could survive a Soviet first strike, but also proved that keeping live weapons aloft for 24 hours inevitably led to crashes in Allied or neutral territory. The doctrine assumed that mechanical reliability and crew endurance were sufficient to manage the risk. Both assumptions were tested to failure at Palomares and Thule. The crashes did not trigger accidental war, but they contaminated land, strained alliances, and forced the U.S. to choose between survivable deterrence and controllable risk. The B-52 remains in service, but no nuclear weapon has flown a continuous airborne alert since 1968. The two crashes forced the United States to choose between survivable deterrence and controllable risk. And the doctrine that replaced Chrome Dome assumed submarines and intercontinental ballistic missiles could deliver both. Submarines offered stealth and endurance without the crash risk. ICBMs offered rapid launch without crew fatigue. The bombers stayed in the nuclear triad, but they would no longer carry live weapons on routine patrols. Chrome Dome proved that some risks could not be engineered away, and that the cost of deterrence could be measured not only in budget and readiness, but in plutonium scattered across Allied farmland and Arctic ice.